Great. So I think I'll launch straight into it. I'm a neuroscientist. I'm based at University College London in the UK. And I try to understand the role of brain in development of pathological fatigue. So I'm sure fatigue is a term that everyone is familiar with. We've all experienced it. And it's something that fluctuates throughout the day, throughout the week, month, year. So there is a lot of nuance to fatigue and how we experience it. But what I'm particularly interested in is for you and I, we know how to alleviate our fatigue, have a good night's rest, good some food to bring up our energy levels, or try and motivate ourselves by switching tasks. So there are different ways of trying to alleviate fatigue. But, and of course, when we think about fatigue, the first thing that comes to mind is, oh, I've probably overworked, or I'm lacking energy, or I'm lacking sleep. So these are the sort of obvious causes of fatigue in someone who doesn't suffer from a disease. But fatigue is not something that it's just felt by people on a daily basis, but in those people with chronic illnesses, fatigue is a feature that doesn't go away. So it is persistent, it is irreversible, it is something that sleep does not alleviate, nor does rest or trying to switch tasks or bringing up your energy levels. So it's something of a mystery, so to speak. And pathological fatigue has been sort of discarded from the scientific area of research on the terms that, oh, this is a subjective phenomenon. Fatigue means different things to different people. It's very hard to get a grip on what we mean by fatigue. So just quickly looking at what sorts of diseases present with persistent fatigue: cardiovascular illnesses and autoimmune disorders. Autoimmune disorders is one of the wide-ranging group of disorders, which includes both neurological and inflammatory conditions. And cancer fatigue is also another huge area. So you can imagine that fatigue is probably caused by different problems in these different groups of diseases. And no matter what the causes, there is always one group of patients within each of these disease conditions where fatigue is unexplained. And especially within neurological disorders, it's quite difficult to pinpoint where the origin of fatigue is. And that's what I'm particularly interested in. And what I study is fatigue in stroke survivors. But fatigue is also a huge problem in other conditions, such as multiple sclerosis and Parkinson's disease and traumatic brain injuries. So these are the sort of major neurological conditions that present with fatigue, which has very little explanation, so to speak. Ooh, sorry. Okay, so I started off with this idea that fatigue that is unrelated to energy levels, fatigue that is unrelated to exercise, and fatigue that is unrelated to motivation, it must originate somewhere. If it is not of peripheral origin, it must be of central origin. And when I say central origin, it is originating from the brain. So how does the brain conjure fatigue? So that was basically where I started off. And if you think about what it is that is presented to the brain on a daily basis, all of these different arrows represent sensory information. Sensory information in the form of visual information, auditory information, tactile information, smell, tastes. So at any given point in time, the brain is being bombarded with tons of sensory information. So how do you make sense of the world? And the idea, a long time ago, the idea was that as and when the sensory information goes in, it is being processed and we act on all of these sensory information. But we know that is now not a possibility because there's just way too much sensory information for if the brain processes all of the sensory information, we would literally be, I don't know, just getting out of bed is going to take us 10 hours because there's so much sensory information that comes through different senses. So how does the brain deal with all of these barrage of sensory information? So what it does is it basically predicts the expected sensory information, and it chooses what information to process and what not to process or ignore. And this is a fundamental principle of how the brain works. So the brain chooses to only process a very small part of the sensory information that is thrown at the brain. And how does it choose? So the choice has to be made by some sort of a prediction. For example, you're listening to my talk. I'm sure there's some background noise that, you know, the heater is humming away, and there are other noises that's coming in. But what you want to do is you want to focus on the talk, or at least that's what I hope you'd be doing. And therefore, you would be filtering out all of the other noises. So by making a prediction in terms of where the noise, the source of noise that should be processed, the other sources of noise would be suppressed. So this is, again, a fundamental rule that applies for all sensory input. Visual input, you're looking at the visual input, there's a lot of clutter in the background. However, you're not going to pay attention to that because you know that what's important to you is the person speaking rather than what's happening in the background. So you suppress task irrelevant information, and in some ways you actually enhance task relevant information, be it visual or auditory. And this happens in relation to somatosensory information as well. When I say somatosensory information, touch. When I move my hand, there is a stretch of the skin, the muscles are contracting, and yet I know that these are anticipated sensory information. So if I move my hand, if I want to move my hand, then I'm going to ignore the skin being stretched because it's basically noise. So sensory filtering is a fundamental rule of how the brain processes sensory information, regardless of the modality of sensory information. So the brain predicts and the brain filters sensory information. This is all well and good, but the theory that I have proposed for, before that, so how does this happen in the brain? So here is a picture of a sensory pathway. This is one of the sort of classic figures that you would see in neuroscience textbooks of how sensory information from the periphery is processed. So you've got sensory neurons from the periphery, that synapse at the spinal cord, and you've got, and it goes up the spinal column all the way up to the cortex. And if you think about, sorry, I thought I had a few more highlights. So let's take, for example, sensory information from the skin. There is a synapse at the spinal cord level. And when I say a synapse, basically this transfer of information from one neuron to another. And where there is a synapse, there is an opportunity to modulate the information that goes up the sensory stream. And it's not just the information that is going up, there are lots of traps that are coming down that also synapses onto these neurons. So how many synapses are there by the time you get to the sensory cortex? You've got one of the spinal cord, one of the cuneate nucleus, and then you've got another stopover at the thalamus, and it goes straight up to the sensory cortex. Now the brain is not 2D. It actually is a 3D structure, and that I've highlighted the sensory cortex, and it's surrounded by lots of other regions. And so these 4 synapses, as it goes up, are not the only stop points, but at each synapse, there's a lot of information that goes in and out of these different junctions. And as you can see, it is surrounded by other brain regions. And similarly, if you look at the thalamus, another relay station right in the subcortical, it's an important sensory subcortical structure, which is surrounded by the basal ganglia, which literally nestles the thalamus. And there are lots of connections between the basal ganglia and the thalamus. And another important structure in the sensory motor system is the cerebellum. So basically, the point I'm trying to make is that there are lots of different junctions for the sensory information before it's being interpreted at the higher cortical levels. And at every junction, there's an opportunity for modulation or filtering of the sensory information. So so for example, depending on, you are paying attention to the sensory information that is coming out from your laptop, but if the fire alarm goes off, there's going to be an immediate switch in attention. So you're going to be filtering out my talk, but you're going to be filtering in the sensory alarm. So all of these are being modulated at different levels. So it's not very simple to pinpoint where exactly the sensory information is being filtered. Hopefully it'll become clear why sensory filtering is such an important concept for fatigue. Right, so basically the theory that I've put forward as an explanation for fatigue that is currently unexplainable is that when the brain is unable to filter anticipated sensory information, then the entire brain is overwhelmed with a lot of sensory input, which then gives rise to this feeling of, oh, I'm so tired. I can't deal with all this information. When you talk to someone who suffers from chronic pathological fatigue, they would say, I cannot go into a pub anymore and hold a conversation because I cannot focus on one conversation. All of the sensory streams seem to be equally processed in my brain. And some of them are quite articulate. They would actually tell this to you. And I've got patients who can run a marathon, but cannot hold a conversation. So that almost suggests that the sensory filtering from the somatosensory system, from your muscles and the body and so the tactile sensation is probably working properly. However, the filtering of some auditory and visual information has gone awry. So sensory filtering is not a single process, and you can independently modulate each of the sensory filtering process. And what I've proposed is that the inability to filter out sensory information gives rise to this feeling of greater effort, having to invest more effort into any given activity, which then gives rise to this feeling of fatigue. So that's a sort of fundamental principle that I've put forward. And if you think about it, it ticks a lot of boxes. For sensory filtration to happen, you don't necessarily need to have low levels of energy. It's got nothing to do with the actual metabolic cost of neuronal activity. And if you think about, have you previously performed an activity for this activity to feel more effort for? That's not the case, because sensory filtering is independent of prior activity, as in it's not the same as post-exercise fatigue. So if we are looking for a cause for fatigue, then sensory filtration is where we should be looking for. And my lab has been studying post-stroke fatigue for quite some time now. And okay. So just to give you an example of, if you ask someone to lift a glass of water, that would be effortless for you and me. But a lot of my patients would say that's like lifting up a weight that's about 3 kilos or so. And why should that be the case? You can imagine if the muscle contraction that is associated with picking up a glass of water, as simple as that, if you process all of the information, then it would give the semblance of high effort, because even low-level muscle contractions, when processed, does feel more effortful. And one thing patients always report is my fatigue after stroke is very different to the fatigue before stroke, or before the onset of whatever disease that they have been suffering from. And that clearly points to the fact that for someone who hasn't experienced this sort of non-filtration of sensory information, it's difficult for them to imagine what it is like to perform an activity when you're unable to suppress anticipated sensory information. So it's quite revealing to talk to patients and how stark the difference is. And as an example, I think in acute inflammatory conditions, for example, you're down with a virus or something. So acute inflammation also gives rise to this kind of fatigue, where you're light sensitive, you're heat sensitive, you just want to curl up in your bed and have a hot cocoa or something. And that's because you don't want to take in any more sensory information. And sometimes, bright lights can be quite too bright for people with fatigue. Okay, so poor sensory filtering of muscle inputs can give rise to high effort, but how does that translate into fatigue? And I think the key lies in how the brain infers information. So one of the hypotheses about how does the brain work is that the brain works by prediction, and it also predicts and it infers the cause of sensory events. So all my retina is seeing is just a jumble of dots of different colors. But what the brain does, it's inferring the fact that there is a human being that is being put together by these pixels of colors that I'm able to see on my retina. So if we were to apply the same principle for high effort, so when someone is doing an activity, you don't expect an activity to be effortful, but if it is, there must be a cause for the effort. So I must be fatigued. So basically the brain is telling itself that it is fatigued in the absence of any obvious cause, like what you would think is, lack of sleep or lack of energy or whatever else. If I'm feeling something to be more effortful, surely it must be because I am tired. And that's how people with pathological fatigue experience fatigue despite no obvious cause for fatigue. And I think I'll probably stop there. And I've just listed out, by lab members, people who worked for me before, and I've also listed out a couple of papers that I have recently published where I've discussed the sensory attenuation hypothesis of pathological fatigue. And that's a picture of the building where I work at Queen Square. And if you're interested, we have been doing sort of public engagement activity, trying to understand the experience of fatigue from a patient perspective. And we have developed an artwork, which is online. And you can go and look at this website, NSNAD, and how patients describe what it feels like to be chronically fatigued. And that's my lab's website. Anyway, I'll stop there. I'm not sure where I am. Probably it's too short a talk, too long a talk, I don't know.
About perfect. Thank you very much, Anna. We have 5 minutes now for any questions anyone may have. You can put your hand up in the function, in the hand up function, or you can write it in the chat. Any questions from people? Gemma.
I think Matthew was first.
Matthew clapped.
Matthew was clapping, yes, but I have a question as well if you want.
Yes, you go on.
Go for it, Gemma.
Oh, you were clapping. Oh, I see. Thanks, Anna. That was great. I mean, when we were together in a conference of Wellcome Trust in 2017 in Beijing, and we had just started our lab like 6 months ago. It's so nice to see how the model has evolved. I was wondering, just very quickly, like, of course, we are in the COVID-19 pandemic, and fatigue has been one of the main symptoms, and people, a substantial proportion of people have long COVID, and it seems like one of the main things is this fatigue. So I was wondering if how your research, if you've done anything like that, or how it informs what's happening with COVID.
We haven't actually directly done any hands-on research. We have been trying to start up a study and getting a feel for, what the experience of fatigue is, and does it actually match up with the sort of sensory basis for fatigue. And we've only just got data coming in. We haven't really got much of handle, but it does sound like it is very much like, people have a good meal, they're eating 3 times a day, they're having good night's sleep, and yet they simply cannot, they describe it as brain fog. And maybe it is brain fog, because clearly if I'm talking about sensory overload, it's just clouding everything in the brain. So it might well be quite a similar process. I haven't touched upon, I don't study chronic fatigue syndrome, but chronic fatigue syndrome mostly tends to be post-viral fatigue. And post-viral fatigue is very much within the remit of, like COVID falls within the post-viral syndrome, I guess. So over time, it can be subsumed within that. I haven't started studying chronic fatigue syndrome per se. It's quite controversial, because as soon as I say the origin of fatigue is in the brain, it always gets interpreted as, oh, well, it's just in my head. It's not real then. I'm like, no. That the brain infers, it is a perception, but the perception is real. There's nothing to say that it is, you're just making it up. So I'm kind of a bit sort of, oh, am I going to get into chronic fatigue syndrome or not? But COVID fatigue is probably within that sort of post-viral syndrome category.
Yeah. Thank you.
Okay.
Matthew.
I had 2 questions. One, how can you distinguish with certainty that someone is really fatigued and not in the other categories So you were eliminating a number of things, but it's hard. I would imagine it's hard to really ensure that they're really the patient you want to look at and not someone else's problem. And two, if I can tack this on, what can you do about it? Are there drugs that are directed at specific neural pathways or junctions in such a way that you can encourage filtering or something, or you're not that far yet?
Yeah, I think we are quite far from it, because yes, I keep getting asked the question that, you know, what can we do about it? Can we actually change this filtering process? And again, filtering is not in a single synapse. Like I say, it is modulation of connectivity within a network of systems, and it may not be neurotransmitter specific. Yes, dopamine has been implicated in the sort of reward circuitry, which again is a filter. Reward is a filter, attention is a filter, and movement is a filter. So there's quite a lot of we can target, but we are still not at that stage. Yes, I'm only testing the theory, so hopefully it will turn out to be true, and then we can start looking at targets. But distinguishing between fatigue and closely related problems, fatigue and apathy tends to come up quite a lot. But the distinct difference between apathy and fatigue is fatigue people are highly motivated. They are quite separate. The reward sensitivity is quite intact. So they want to do things and they're unable to do things. Whereas in apathy, they can't be bothered if they do something or not. They're like, meh, I'm not going to do anything. So it's relatively easy to distinguish fatigue and apathy, although there are overlapping traits. And the other thing is depression. Depression is a huge overlapping factor of fatigue. And you do see they occur together in a lot of conditions. In stroke, you've got depression and fatigue overlapping by about 80% actually. But the problem is people have tried SSRIs, like serotonergic drugs. That's your first stop for treating depression. It seems to improve scores of depression, but then fatigue remains the same or it gets worse. So there is something, it's definitely not serotonergic. Modafinil seems to, it's a dopaminergic drug. That seems to have some effect, but only in a selected group of patients. So I'm beginning to think there is actually, you know, when I talk about sensory filter, when movement is your sensory filter that's gone wrong, it's a very different type of fatigue to when your reward filter has gone wrong. So modafinil might probably work for someone whose reward sensitivity is decreased. So the field is really muddled up. We do need to try and work out what are the phenotypes of fatigue, so to speak, where then we can start to say maybe the mood-related disorders fall under the same category, where fatigue and depression, when they overlap, it's probably got something to do with dopamine reduction. But it's not the same when movement is your sensory filter has gone awry, and we still don't know what the sort of targets are. I don't know, I'm just giving another sort of too long-winded answer.